Hello, everyone. Welcome to an exciting journey into the world of work, energy, and power. Now, imagine you're pushing a shopping cart, you exert force on it, and voila, it starts moving. We've all done this, right? But what if you push as hard as you can and it doesn't move? That's not work in the physics sense. So, let's define it. Work is the transfer of energy when a force acts on an object and makes it move. Let's break it down with the formula. Work equals force multiplied by displacement multiplied by the cosine of the angle between the force and the direction of the displacement. Now, let's make sense of this. Think of it like this. Imagine you're pushing a box. If the box moves in the direction you're pushing, you're doing work. But if the box doesn't move, then no work is done. It's a bit like trying to push a car that's stuck in the mud. You push with all your might, but if it doesn't move, no work is done, even though you're applying force. The unit of work is joules, named after the scientist James Joule. So, next time you're lifting heavy groceries, remember, you're transferring energy. Cool, right? Alright, moving on to kinetic energy. This one is a lot of fun because it's all about motion. Imagine you're riding your bike down a hill. The faster you go, the more energy you have. That's kinetic energy in action. The formula for kinetic energy is kinetic energy equals 1/2 multiplied by mass multiplied by velocity squared. So, if you're riding your bike, the mass is your body and the bike combined, and the velocity is how fast you're going. Kinetic energy depends not just on how fast you're going, but also on how heavy the bike is. Here's the kicker. Kinetic energy increases with the square of the velocity, meaning if you double your speed, your energy quadruples. So, if you go twice as fast, you don't just double your energy, you quadruple it. No wonder why cars and roller coasters are so fast, they have tons of energy packed in. Now, picture this, a truck and a car. The truck might be slower, but it could still have more kinetic energy if it's heavier. So, in the world of physics, bigger mass and higher velocity equals more energy. Now, let's talk about something that connects work and kinetic energy, the work-energy theorem. This is where things get pretty interesting. Have you ever wondered, how does applying a force change something's energy? Well, the work-energy theorem says the work done on an object equals the change in its kinetic energy. In simpler terms, if you push something and it starts moving, the work you do on it turns into kinetic energy. Imagine you're giving a push to a skateboard. You apply force, and the skateboard speeds up. That's work turning into kinetic energy. So, if you push a cart, the energy you put into the cart is stored as kinetic energy. This is super useful in real life, like when you're pushing a car or even when you see a rocket blasting off. The force you exert results in a change in speed, and that change shows up as a change in the kinetic energy of the object. Let's make things more exciting with an example. Let's say you have a 2 kg block. You apply a constant 10 Newton force to move it across a distance of 5 meters. How much work is done on the block and how much does its kinetic energy change? Here's how we figure it out. Work equals force multiplied by displacement. So, work equals 10 newtons multiplied by 5 meters, which gives us 50 joules. That's the energy transferred to the block, and since the work done equals the change in kinetic energy, the block's kinetic energy increases by 50 joules. Now, picture this. You gave this block 50 joules of energy by applying force over that distance. 50 joules is now the energy the block has in motion. So, work equals change in kinetic energy. Pretty simple, right? Alright, what if the force is not constant? Say you're pushing something and the force changes along the way. That's a real-life scenario. Maybe you're pushing a shopping cart and you start out easy, but the cart gets heavier as you load more stuff. In that case, we still apply the same concept, but we have to use an integral to account for the changing force. The formula for this is work equals the integral of force as a function of displacement over the limits of displacement. So, when force varies along the way, we sum up tiny amounts of work done over each small displacement, just like adding up tiny areas on a graph of force versus displacement. In simple words, we find the area under the force displacement curve. This way, even if the force changes, we can still calculate the total work done. If you've ever pushed something where the resistance changes, like a bike going uphill with varying slopes, this is exactly how we can calculate the work done. To wrap things up, we've learned a lot today. Work is the energy transferred when a force acts on an object and makes it move. Kinetic energy is the energy an object has due to its motion, and the work-energy theorem tells us that the work done on an object is equal to its change in kinetic energy. These ideas are everywhere, from the bike you ride to the cars you see on the road and even in the physics behind rocket launches. Work and energy are what make everything move. So, the next time you're pushing a cart or speeding down a hill, think about the work you're doing and the kinetic energy you're adding to the system. Physics is all around us, and it helps us understand how the world moves. I hope you enjoyed this session and feel confident explaining work, energy, and power. See you next time with more exciting physics that explain the forces that shape our world.